Welcome to The Explainer. You ever stop and think about how services like Google Maps or Waze do what they do? How they can look at a bajillion possible routes and, in just a few seconds, find you the absolute best one? Well, today, we're going to pull back the curtain on the elegant and actually pretty simple logic that powers that everyday magic. You know, this whole problem of finding the shortest path, it's not new at all. We've been trying to figure out the most efficient way to get from point A to point B for, well, forever. Whether it was following a big landmark highway like Route 66 or just navigating by the stars. It's just something we've always been trying to solve. Okay, let's really dive into this. If you look at a map of a city, finding a decent path is pretty easy. But the best path, the one that is guaranteed to be the shortest, no questions asked, that takes something special. So how in the world do we build an algorithm that can actually promise that kind of perfection? We're going to start with a really simple, common sense strategy. It's often called branch and bound, and you can think of it like a very, very meticulous explorer. Super thorough, but maybe not the cleverest explorer out there. So the logic here is actually beautiful in its simplicity. Just picture you have a bunch of different partial routes you're exploring at the same time. At any given moment, you just ask one question. Of all the paths I'm currently working on, which one is the shortest so far? And then you just take one more step down that path. You just keep doing that over and over, always focusing on the path with the shortest running total. And you know what? For a small, simple problem, this works perfectly. It feels right, it checks the most promising options first, and it always finds the guaranteed shortest path. So far, so good, right? But here's the thing, the real world isn't a simple little diagram. It's this huge, sprawling, complicated mess of streets and highways and weird one-way alleys. So what happens when we let our simple little explorer loose on a map that looks a lot more like an actual city? Yeah, this is where it just hits a brick wall. On a more realistic map, our simple branch and bound method just explodes. It ends up exploring 835 different path segments before it finds the answer. I mean, it gets there, sure, but it is painfully inefficient. It's just doing way, way too much work. All right, so clearly our brute force approach needs a serious upgrade. It's got the brawn, but it has no brain. So let's see how we can level up this algorithm with two really clever improvements that are going to completely change the game. So our first upgrade is basically giving the algorithm a memory. We create something called an extended list to keep track of every single spot we've already been to. Now, if we find another path to that same spot, but it's a longer path, we just ignore it. Simple rule. Don't do the same work twice if the result is worse. The second upgrade is what's called a heuristic, which is just a fancy word for a smart guess. We give the algorithm a little hint, the straight line distance to the goal, as the crow flies. This helps it focus on paths that are not just short, but are also heading in the right general direction. Now let's see what happens if we just apply that first upgrade. The memory. Get this. We slash the number of explorations from that painful 835 all the way down to just 38. That is a massive, massive improvement just from not being stupid enough to do the same work over again. Okay, so what about our smart guess? Well, using that airline distance heuristic all by itself also gives us a huge boost. It cuts the work from 835 down to 70. Now, in this particular case, it's not quite as good as the memory upgrade, but it's still an incredibly powerful tool. So we have two fantastic upgrades, right? One adds memory to stop wasted effort. The other adds a kind of foresight to guide the search. So the obvious question is, what happens if we just use them both at the same time? Well, that is when we create something truly special, the legendary A** algorithm. A* or A* is pretty much the gold standard for finding paths. It's our original simple strategy, but it's completely supercharged. It still looks at the actual distance traveled, but it adds that smart heuristic guess to help it decide where to look next. And the crucial part, it uses that extended list memory to make sure it never ever wastes time exploring a place it's already found a better way to get to. And the result, when you combine these two ideas, it's just stunning. With A*, our algorithm solves the exact same complex map by exploring only 27 segments. 27! I mean, that is the difference between an algorithm that's just a cool idea in a textbook and one that can actually power a real-time app on your phone. This chart right here just tells the whole story perfectly. Look at that first bar. We started with that brute force method, which was just incredibly slow. Then, adding either the heuristic or the extended list gave us a huge speed up.
But putting them together to create A star, well, that little bar at the end is the undisputed champion. It's not even a contest.
Okay, so A star is perfect, right? It's the best, it's super efficient, problem solved, we're done. Well, not quite. Like any really powerful tool, there's a hidden catch. There's this one specific kind of scenario where our smart guess can actually lead us completely down the wrong path. You have to remember, this whole idea of search isn't just about geographical maps. It's a way of thinking about any problem where you have to make a series of choices to reach a goal. And in some of those more abstract problems, our little smart guess heuristic, the thing that seems so helpful, can actually be tricked. So this right here is what's called a pathological case. It's a very specific trap designed to make A star fail. Now, look at step 1. The path from S to B looks amazing. Its actual cost is 1, and its guessed cost is 0, so the total is 1. The path from S to A looks terrible in comparison, a cost of 101. So naturally, A star explores the S to B path first, and it eventually finds a route to the goal with a total cost of 111. But here's the killer. Because it already reached that point C through the bad path, its memory, that extended list, stops it from ever even considering the real shorter path through A. The smart guess tricked it, and its own memory locked in the mistake. And there it is, the failure. Our trusted, supposedly optimal A star algorithm found a path of 111 when a much better path of 102 was sitting there the whole time. It was just so confident in its initial bad guess that it never bothered to go back and double check. So how do you fix that? Well, the solution is a stricter rule for our smart guess. It's called consistency. And to put it simply, it just makes sure the algorithm's optimism stays in check. It says that as you move from one point to the next, your guess about the remaining distance can't suddenly get way, way better than the actual cost of the step you just took. It basically prevents the kind of logical trap we just saw. So let's just recap this whole incredible journey. We started with a really simple but really slow idea. We then looked at its weaknesses and bolted on 2 powerful upgrades, memory and foresight. We combined those to create A star, which is honestly one of the most important algorithms in all of computer science. And then we even found its one subtle flaw and discovered the final piece of the puzzle, consistency that makes it truly foolproof. And that's really the coolest part. The logic of A star isn't just for your GPS. It's the same kind of thinking used to figure out the best moves for an AI in a video game, or to route data packets across the internet, or to solve massive, complex logistics problems. This quest for the shortest path, it's absolutely everywhere. Thanks for watching.
Follow for more.